when Gurdip stops and asks for questions. On that note, the floors are yours, Gurdip. Um,
Well, thank you for having me here. Um, so, when I started thinking about this paper several years ago, one of the things that came to my mind is that most people, when they talk about the expected rate of return, is supposed to be a conditional estimate. And people need to contrast between the average rate of return and the conditional expected access rate of return on the market. I mean, it's an important number. It's actually used in a number of applications, and and much of our research relies on the conditional expected access rate of return on the market, but it's actually not observable. So we thought about how can we back out this number from options, and about the same time Martin's a well received paper was circulated, and he actually derived a lower bound on the expected access rate of return on the market. So what we wanted to do was to compute essentially an estimate of the value for the conditional expected access rate of return on the market, and essentially get it from option prices. And when we were working on this, it turned out that we can derive a formula which will depend on all higher moments, all higher central moments. And I think at some point in time, CBOE will come up with these estimates on a daily basis so that we don't really have to do it. So in that sense, in this formula, May is an interesting development, because some of the estimates can easily be inferred from option prices. And now, as you know, we have more than 100 to 150 options available. So the estimates of these central moments are going to be very, very accurate and reliable. So and one of the things that we're gonna emphasize down the road and somewhat aggressively is that we will derive this formula without needing the negative correlation condition, which I'll be talking about shortly. We'll also study the asset pricing restrictions on the NCC, because it's kind of a black box. I mean, conditional covariances are not really observable. So if you make an assumption that it's got a certain property, what are the restrictions, and how do you test in the data, and what models are consistent with the NCC? That's something that I'll be talking about today as well, as we have time. So just to very quickly, I'm going to be using P moments, Q moments, and RT is just the rate of return. And I'm also going to define an STF, which is the big STF, which is going to price everything by MT. But I'm going to essentially look at a narrower STF, which is essentially a projected STF, which hopefully prices all returns in the market. So it's a subset of the STF. And in general, I'll be focusing on the projected STF. And Z over here is essentially the gross return vector contingent on RT, like, for example, option returns, straddles, strangles, butterfly spreads. They will all be contained in this vector Z. So here is a negative correlation condition. It basically says that if you take the STF multiplied by the market return and you look at its covariance with the market, then it should be negative. So that's an assumption that Martin made, and Martin's paper is now well liked, and that's the assumption that he made in his paper. So I'm essentially articulating this particular condition, because he will have a bound which is on this page, that once you make this assumption and you use the definition of covariance, and you say that the minus the covariance with MTRT and RT is positive, I mean, the bound pops out with the with the stipulation that you can back out this conditional variance of the market under Q from option prices, and you're essentially spanning. And he's looking at the simple rate of return, which is ST over ST now minus one, whereas most people in the past had looked at the log in a conditional variance. So this is the lower bound, and this is the formula, because you can easily back out the conditional variances from the market. So this is essentially the discounted, risk neutral variance of the market. And if you annualize it, multiply it by 12, and then take square root, that will give you an estimate of the conditional expected excess rate of return on the market. And in his, estimations, the way he did this is that he actually took estimates from 1 month, 2 month, 3 month, all the way to 5 or 6 months. And then he put a linear curve and said that this is your estimate of the conditional expected excess rate of return. It's a bound. And then he also went ahead and showed that the conditional covariance says in his setup, they were essentially close to 0. So the bound is tight. So on the other hand, as opposed to this formula, we are going to develop a formula which will have all higher moments embedded in there. And there's some trade-off between his approach and our approach, but the big idea is to essentially develop a formula and not a bound for the conditional expected excess rate of return of the market. So just like I said, I mean, and it does not depend on whether the NCC, our formula does not depend on whether the NCC holds or not. So as I will show you, and I will comment on it on this shortly, we are using projected STFs. So what that means is that we are assuming that the M is only a function of RT. So why are we focusing on STFs that are a function of RT? First of all, I mean, when it comes to considering claims that are written on the market return, it actually suffices to work with the projection of the STF. I mean, we have a small result in the paper that shows this. And this result is actually quite important, but it's not fully appreciated that, that you can just work with the projection. So it means that if you are in one of the 3 models, like a habit formation model, and you try to go through that route, I mean, you're not going to be able to get exactly a conditional expected excess rate of return because it's based on consumption, whereas we are essentially using option data to actually derive this conditional expected excess rate of return. Now, second of all, Martin shows the special case that if MT is equal to 1 over RT, which is the log utility, then the covariance term or the NCC will be exactly equal to 0, and the bound is going to be tight. So from now onwards, we will use this projected STF without loss of generality. All right, and we are making some assumptions on this projected STF, and this all goes back to Rosenberg and Engel 2002 and maybe others. But that's one paper that I'm aware of that made this point a little bit more precise. All right, so here is the assumption that I'm making about MT. Look, I mean, our formula is in the spirit of bond pricing models and option pricing models and other formulas in finance, that you have to make some assumption. And we will argue that the bound that we are extracting from the data and comparing it to our formula will be very, very far, that the bound is going to be very, very far off compared to the estimates that we are getting from our formula and many formulas. I mean, this is not the only formula that we are developing, but this is a very convenient STF because here the log of the M is linear in the excess rate of return. I mean, you can use more general M's by putting in volatility and estimating them. But as you will see, this M is essentially exponential in a factor. You can add other factors, and we will show you that some of the minimum discrepancy problems can be used to really estimate this fee from the data. And we will, and it's going to be data informed. So here, once you make this assumption about MT, we are going through the math in terms of the cumulants under P and the cumulants under Q, and the proof of that is in the appendix. But once you go through that, then the conditional expected excess rate of return on the market under P will be it's going to have a series solution where it's going to depend on all higher moments. Which moment is important, we can actually figure it out from the data once we know an estimate of fee. I mean, in general, we will show you that fee is about 2.2 in the data and is very reliably estimated. And it will give us reasonable estimates of the expected excess rate of return. It will meet a smell test. I mean, it's a very aggressive way of saying that this formula is there, because in the past we have only been able to derive a bound on the expected excess rate of return, but now we have a formula, and this formula can be very, very flexible by using different forms of M. I mean, just like in option pricing and bond pricing, we use many, many different models, and we look at empirical performance. But the task over here is a little bit more difficult because expected excess rate of return is not observable. So you can only use this formula to figure out, is the number small or large? What other puzzles can you understand in the data? What does it say about term structure of the expected excess rate of return? Or how does it vary over FOMC, even week cycles? How's it varying on a daily basis? But the point is that you have a formula, and it will depend on all higher central moments of the excess rate of return. And these moments are essentially data driven. You can extract from the data, from the option data, and hence you have a conditional risk premium estimate over here. I mean, of course, our experience has been that that if the information in the market is changing, then they are getting reflected in the option prices. Then your estimates of the conditional expected, then the estimates of the conditional expected rate of return are going to be a little bit more well behaved. I mean, it's like this: if you make an estimate of the conditional expected, excess rate of return at the end of the month, and then you try to essentially evaluate that estimate relative to some benchmark or some other yardstick, and 1 month later in a predictive exercise, but a lot has changed in 30 days. So it means that if you do it on a daily or a weekly basis, you will have a much better sense of the predictability that's coming from this conditional expected excess rate of return than to do it on a very long spaced intervals. I mean, it's like volatility. I mean, if you try to predict volatility on a monthly basis and a lot is changing, then your volatility, estimate of the future volatility will be less accurate. So with that said,
can I interrupt here for a minute, because there are a couple of questions that I think it makes sense to take before you leave this slide.
Yes.
So one from Ivan Shaliastovich: if the conditional covariance of log M with R is constant, isn't it almost like a risk, like the risk premium is constant up to? Oh, he just amended his question. Oh, let's forget it then. Okay. From Bing Han: can you expand the specification to account for non-monotonic log projected pricing kernel?
Yes, we have some examples. In fact, we have a very, very general result. You give me a specification of M where one of our M is infinitely differentiable, then I can give you a formula for that. It's going to be less parsimonious, but it is a formula. It's coming.
And then from Peter Carr, which is, I think, a comment, the implicit assumption that all higher moments are finite rules out distributions with power law tails. Do you want to respond to that?
I don't know. I mean, yeah, if the moments are exploding, then things will explode. I mean, it does not matter from an empirical perspective because you're just backing it from the data. You're not making any assumptions about what the underlying P density is. You want the first four moments of the P and the Q densities to be well behaved. So the first four moments have to exist.
Okay, I'll let you and Peter take that up at the end. Oh, go ahead.
I mean, you can't say you're not making any assumptions and then say the first four moments have to exist. I mean,
well, I mean, there has to be some assumptions for the cumulants to be well behaved under P and Q. If they are not well, I mean, so essentially the standard assumption is that the first four moments of the P density of R, they're well behaved. Yeah, I mean, not well behaved.
I was objecting to the statement that you're not making assumptions. You are.
Well, oh, okay. I mean, it is there in the proof. I mean, we have those assumptions in the back about some of the regularity conditions and some other assumptions for the densities to be well behaved. Yeah, but in fact, I mean, we are just backing out these moments from the data. They are in the data. We just back them out.
Yes, you are. But if you try to back out moments from data that when the population moments don't exist, you're not going to estimate them, right? So you just it doesn't make sense.
Well, yeah, there is an assumption in the back that the first four moments under P and Q they have to be finite.
Right. Okay.
I mean, here I go to the fifth, but it is implicit. I mean, in there, for example, if you're using some of the Mandelbrot type, distributions, then some of these moments are exploding. Yes.
Okay.
Okay. Let me move forward. All right. So as you can see, this is expressed as an infinite series, and you want the phi times the standard deviation to be less than 1. But since, for example, the standard deviation under Q of is about 0.03 or 0.05, then phi times the standard deviation. So the phi has to be very, very large for this thing not to converge. In the monthly data, it's not a problem. So this is an infinite sum. You have to truncate it, and I'll show you some numbers. As you go higher and higher moments, I mean, you're not even adding 1 basis point at the very end to the fifth moment to the expected access rate of return. So I will talk about that. So we have a new formula, and it's not a lower bound. And all you really need is central moments of the access rate of return. And the math for the formula is in the appendix. We have some additional assumptions. But this is a very, very attractive class of M's, which are exponential. So, I mean, if you take a Taylor series of the exponential, I mean, all polynomials are showing up in here, which is kind of, I mean, akin to what Trajani and Schneider also looked in their Journal of Finance paper as well. But here we have an exact formula, and it's not a bound. All right. So what is the justification? I guess we have talked about the justification a little bit based on the questions. But so the way that we are thinking about this is that this MT is economically motivated because it's coming from an explicit minimum discrepancy problem. And these minimum discrepancy problems are getting popular because you can extract a model-free way the M's, but we're not really extracting the M's in a model-free manner. We are just using it to estimate the phi, which is unknown. Look, I mean, a no approach is going to be costless. I mean, you have to make some assumption. I mean, in the bound may not be tight, but it's model free. Over here, the phi has to be estimated, but the model may be more reliable. It may be, I mean, it's a formula, it's an exact formula. So there are always these trade-offs when you think about deriving exact formulations. But over here, the minimum discrepancy problem that leads to the form of M is x log x, subject to correct pricing. So you can see from here that the optimal solution M star is just exponential in the access rate of return, where you can essentially use a one-dimensional optimization to estimate phi and M0 from the data, and they are so in our and also you can get bootstrap standard errors. So over here, the phi is 2.274 with a 90% confidence, bootstrap confidence interval 1.30 and 3.29. So with this, I mean, estimate over a long time series, we can actually implement a formula, back out these moments from the option data. We have lots and lots of options. We can get these higher moments easily from the data, and then input into the formula, compare it to the lower bound and some other way, and then do some other exercises that I'll talk to you shortly about. All right, so let's see. So the first of all, I mean, does this formula meet a smell test? I think that's the most important thing that we thought about. So when we implemented this model over approximately a 30-year sample from 1990 to say December 2018 in option expiration cycles, the annualized average expected excess return was 8.97%. Now it's got some considerable time variation, because as these moments are varying through time, the conditional expected excess rate of return will change as well. So you have a large band between the 5th and the 95th percentile values, and on average, I mean the 8.97% that we're finding compares well to the 7.81% over 1926, 07 to 2018, 12. I mean, in fact, if you estimate the expected excess rate of return on a daily basis, you can do better. And that way you are much closer to the average rate of return that has been historically observed. So let me just show you some numbers, and then I can take some questions. But you know, but here is the difference between the equity premium and the lower bound. Why is this important? Because if the lower bound was tight, then there should be no difference between the equity premium and the lower bound. But as you can see, there's a large amount of variation between our formula-based equity premium and the lower bound, which only depends on the variance, on the Q variance. Now you can see from here, from the formula, that our formula would be approximately 2 times the variance. So, as compared to the lower bound, which is basically a discounted risk neutral variance. So it means that our estimates are almost 2 times the lower bound, minus some of the risk neutral skewness adjustment. So here you will see that since the risk neutral skewness is negative, whereas the kurtosis -3 is generally positive, here the second term will lower the expected rate of return, whereas the third term will make it higher. So all odd moments will lower it, and all even moments will make the expected excess rate of return go up, at least according to the formula. And that's something that we are observing, and I will show you some numbers shortly. So here are some of the numbers where we are looking at some of the contribution of the terms. So you can see from here that the skewness and the volatility terms are essentially accounting for much of the variation in the formula. Whereas the fifth moment is only less than 1 basis point, and the fourth moment, central moment normalized, is about 5 basis points. So you can see from here that the tails may matter conditionally, but on average, they're not mattering as much in terms of the average expected excess rate of return. So the 2 important terms are basically coming from the variance weighted. So here you can imagine that the way that we derive these cumulant, relationships, I mean, these weights are actually coming from the weighting of the densities. I mean, how you move from P to Q is actually weighting some of these Q dense moments, and they're naturally showing up as a part of the P to Q mapping that is there in the appendix. And then we're using the cumulants, and then from the cumulants we're going to the moments. So in fact, you can actually derive the conditional expected excess rate, the conditional expected mm, um, uh, moments under P in terms of option prices as well, even though we are only focusing on the first moment, which is the first moment of the returns. So, I mean, on average, the Martin lower bound is 4.32% as compared to 8.97% from a formula. I mean, the 4.3% is actually close to what Martin had in his paper between his sample period was, I think, 1996 to 2012. He had about 5%, and we are getting 4.32. But so these are the major differences that you can see from the data. Is also showing that the conditional covariance term is actually as important as the lower bound, or even more important. And I'll also talk about this thing shortly by looking at the data over the FOMC cycles, where I can identify the covariance term a little bit better. But essentially, I mean, here the conditional covariance term is no longer a black box. You can infer it from the option prices using a formula minus this lower bound that will give you the conditional covariance that Martin has in his paper. All right, so this is something that we did with the monthly data in expiration cycles. And we also estimated the model on a daily basis. But as you know, on a daily basis, you cannot really have a constant term to maturity. So the term to maturity is going to be varying. So we will essentially estimate the expected excess rate of return on a T period basis, and then we annualize it so that we can compare it to the monthly data estimates. So we implemented the formula over 7,293 days. And we were very, very careful about the estimation of the higher moments, because they can be unreliable. It's not really a problem since 1996, because we had lots and lots of data on the option strikes. So you can easily get the higher moments, but still we were very, very careful. And here we're getting a sample average of 7.81%, which is very close to the data over the past, say, 100 years or 90 years. In the daily data, we get a lower bound estimate of 3.59%, which is about half of our formula-based estimate. But the key point that we wanted to emphasize is that as and when CBOE gets these estimates to us on a daily basis, if they do it, sometimes they do it, sometimes they don't do it. But then you can essentially get a day-by-day estimate of the equity risk premium based on very, very reliable estimates of the higher moments that CBOE can directly provide. We try to do a very careful job over here so that there are no outliers, or we were trying to figure out why the outliers were there, why there were data errors, and blah, blah, blah. So we fixed all of that. And our estimates are actually well behaved, even on a daily basis. All right, so this is the daily estimates. Now, before I get to the next step, I just wanted to explain a little bit, which most of you know, that is that much of the daily volume in open interest is actually concentrated in the first 4 maturities. And I'm showing these numbers because in the next step, I'm going to look at the term structure of the expected excess rate of return. So I'm going to go in option expiration cycles 1, 2, 3, 4, and then I'm going to ask I mean, if I compare the fourth maturity expected access rate of return, properly normalized to the first maturity, will the expected access rate of return be downward sloping or upward sloping? In this particular exercise, I mean, overall from the daily, we have 330,000 option observations. So here is the.
Oh, so could I interrupt and
Yes,
ask if this would be a good time to take a few questions?
of course, of course.
So there were several questions about whether phi is constant and how you estimate it.
Well, I mean, phi
So
is
some models would imply that phi is changing over time.
yes, I mean, we will look at other models, but phi is just coming from the minimum discrepancy problem. I mean, so when we do factor models or the linear factor models, we just have that second moment inversion. So over here, this is quite similar to that, but we're in the exponential space. So over here, m is always going to be positive. So the phi is can be estimated very, very nicely using a one-dimensional optimization that's right here. Okay, so but yeah, go ahead.
But a one-dimensional optimization assuming it's constant. So is it reasonable
Yes.
assume it's constant?
Well, in this particular formulation of m, it's a constant, but you can get other models which are conditional where you can use lagged information. I will get to that.
Okay. Another question related to that, is phi estimated using the same returns data whose means are being matched?
Yes, of course. I mean, so when we did this, we used monthly data from 1930 all the way to now because you need longer periods of data. We did not. I used the estimate over 1990 to 2010 because it can be noisy, and so we essentially estimated the phi by. So essentially the main point of the estimation procedure is to enforce the correct unconditional pricing of the excess rate of return of the market, and we are using about 70 years of data or 80 years of data from 1930 all the way to so yes, so it's going to be 90 years of data approximately.
Okay. And then there was a series of questions that I haven't completely followed about the relation between the equity premium and skewness. So is the equity premium increasing or decreasing in skewness in your model?
So over here, the skewness under Q is always negative. So if the markets become more negatively skewed, that will lower the expected excess rate of return. It's just showing from the formula because the skew is never negative in the data, at least in the monthly data is never negative.
Okay, so then the question was, I would have thought a higher conditional downside risk would increase the equity premium, but this formula seems to indicate that the reverse is true. Can you explain why?
So yeah, so we thought about this particular issue. Let me just try to frame it how I thought about it that time. That if you have this is the Q. This is the Q skewness, not a P skewness, but because people think about lottery stocks and other things that if investors would like to hold stocks that I'm trying to think about how to frame this in my head. So if you have payoffs that are positively skewed under P, then you will require a lower expected excess rate of return because but over here all the relationships are under the Q measure. So the way I think about this is that skew under P will be equal to uh, um, um, so the skew under Q is equal to skew under P minus an adjustment term, because the risk premium on skewness is actually positive. So I think I need a better explanation for why this. I think it's there in the paper, but I forgot what we wrote in the paper exactly. But this is consistent with some of the explanation that we have in the paper.
Okay, so I'll ask one more question and let you move on then, since I see that we're only on slide 9. But anyway, from Peter Carr. Since Jane's maximum entropy principle is being used to determine phi empirically, why not get the whole p distribution of the excess market return instead of just its p mean?
Well, it's not going to be a conditional measure. All right. I mean, we are using options to get the conditional expected rate of return. Yes, you can get that from x log x, but we are looking at a conditional measure.
Okay. But anyway, I feel like I should let you and Peter talk about this afterward and let you move on.
All right. So let me move forward. So I have what, 30 minutes left approximately? Okay, 22. All right. So this is the Binsbergen, Brandt, and Coagent paper, which is very controversial, which is basically saying that they found that short-term dividends, the way that they did it, will have a higher risk premium than the longer-term dividends, whereas the leading asset pricing models predict the opposite. So we wanted to wade into this particular thing and just go and check what is our formula saying about the conditional expected excess rate of return as a function of maturities. So as I said, we are going to look at 4 maturities averaging 26, 56, 90, and 141 days. So our maturities don't overlap with theirs because they're looking at very long-term maturities, 6 months and beyond. So our stuff can be thought about looking at the term structure at the short end versus the long end. So when we say that the equity premium curve is we are really talking about expected excess rate of return as a function of t, which is the maturities, and then we define the term structure as a difference between annualized over period t versus the first maturity. And if that's negative, then we're saying that the term structure is downward sloping. Now you can see from here that when we did this exercise using our option data at 4 different maturities, 56% of the time, if we look at the first row, 56% of the time the term structure was downward sloping, but 44% of the time it was upward sloping. On average, the size of the term premium between 4 minus 1 is 2.2% minus. So it's lower. And so it means that conditionally, in the case of Binsbergen and Brandt and Coagent, I mean, they're looking at an average number over unconditional. But what we are doing is, yes, we can get an unconditional number for the term structure, but we can also ask conditionally whether the term structure is upward sloping or downward sloping, and when is it. So just to get to that particular point shortly, you can see from here that we are offering the insight that the equity premium curve is not uniformly declining or uniformly increasing, but it's switching sign. So it's conditionally changing sign. But on average slope of the equity premium curve is going to be reliably negative. And also average slope of the equity premium is positive when the market return over the prior expiration cycle is positive, or when the quadratic variation of the prior expiration cycle is lower than the sample average. So we're just trying to scratch and dig deeper into when is the conditional expected excess rate of return term structure upward sloping or downward sloping, and why is it switching sign? I mean, the intuition is that much of the market fear is on the short end. So people are more worried about immediate risk as opposed to long-term risk, but that changes over time. I mean, for example, if people are more worried about what's going to happen 3 months from now, like with respect to the coronavirus, then things may change. But in general, people have bets in the short run. They're more worried about short-term exposures. So on average, the expected excess rate of return is higher at the short end versus the long end. So we have done some exercises over here, but we can add more conditioning variables. But the gist of the matter is that that the expected excess rate of return term structure is changing over time. So we now moving to the next topic. I mean, this is one application that we that we looked in this paper for our formula. There may be other applications, but this is an important application in terms of what people are doing these days in terms of trying to understand the term structure of the expected excess rate of return. All right, so now the big question that we have been asked over and over again is, how do you identify that the NCC is not zero? Because I think in the Martin paper, he did some exercises using his models to show that the conditional covariance term on average is zero. So what we did is that we can, it's in our case, I mean, the covariance term is no longer a black box because we can infer it directly from the data. So we have a conditional estimate of this p-measure covariance. So what we did is that we essentially went and looked at the exercise in Ciaslik, Wissing, Jorgensen, and Morse, where we said, okay, can we identify these covariances and how they're changing, I mean, over time, in some meaningful way. So what we did is we essentially took some of the specification, but our focus is to ask, are these conditional covariances equal to zero? And are they changing over time? And what fraction of the expected excess rate of return it can be attributed to these conditional covariances? So we did these dummy variable regressions over week 0 to 4, 6, and also some other week 0 to 4 and 6 separately. And we have the results over here. And you can see from here that the conditional covariances are actually declining over the even weeks as opposed to the odd weeks, and this effect is highly significant. And also the expected or the equity risk premiums are also declining. In the case of Ciaslik and Wissing Jorgensen, what they were doing is that they were assuming that the Martin lower bound is tight, and they were showing that the conditional expected excess rate of return is changing in a direction that is opposite to what the realized rate of return how they were changing, because the realized rate of returns are actually increasing, as you can see in panel number D. So they are positive, whereas the conditional covariance, the lower bound, and the equity premiums, they're all declining. So so the point is that we are deducing a strong reduction in the conditional covariance term over the FOMC cycles, and it's telling us that the extracted covariance term is an empirically relevant component of the equity risk premium. And so a formula is picking up these conditional covariances, which will not show up if you just rely on the bound. So this is another piece of evidence that is essentially showing that the difference between our formula and the lower bound is not small. It's actually as important as the lower bound formula itself. So it means that you're really missing a lot of the conditional expected, is that you're missing the magnitude of the conditional expected excess rate of return if you just use the lower bound formula. Okay, so here is the question that came early on: can we generalize it? So over here, what we did is that if you take 1 over m, and the idea of 1 over m is that you can think about conditional covariances under Q. So you're looking at 1 over m. So this is just the inverse of the radon, the radon-Nikodym derivative in some sense. And you're saying if that is infinitely different, if it is continuous and also infinitely differentiable, then given this function h is only a function of the it's still a projected STF, then you can derive the expected excess rate of return for any function h satisfying the property that we have, that it be continuous and infinitely differentiable. So this will create many formulas which can be taken in the data. But the key thing is that we need, in order to estimate some of the parameters, you have to put it in a certain form where the rate of return of these factors are showing up in M, so that they can be estimated using the minimum so that you can estimate it using the minimum discrepancy problems. So for example, if H was exponentially affine in the excess rate of return, that will go back to the empirical work that we have done based on the exponential function. But you can generalize it to many different ways, and I'm going to just talk about 2 or 3 different functions. So let me first talk about, suppose MT is of the following form, where you're allowing for state dependency. So you have an instrument which is lagged Z, any lag Z. So you are saying if you incorporate additional time variation in MT based on lag information and the current M, or the current in market return, then we can essentially estimate the phi and the phi Z directly using the minimum discrepancy problem. So over here, if you're doing this on the monthly interval, I mean, the only requirement that you have is that you should be able to use daily data on some of these things. For example, you have daily data on the HML factor or the momentum factor or the size factor, or you can use variances. I mean, variances are, I mean, you can just use quadratic variation and essentially construct this on from the daily data. I mean, market variances are quite intuitive variables to enter into M, because as you know that VIX goes up when the markets are doing bad. So your M will be high when VIX is high or the volatility is high. But you can also expand these M to a very large class. For example, you can use the log of R, where if you take a Taylor series of log of R, you will have all higher moments showing up in this M. And where the small p is essentially the price of the log contract. So you can span the log payoff in terms of his price, and that's a return, and you're subtracting the risk-free rate of return. So that's just an excess rate of return on the log contract, and this is essentially the excess rate of return on the market. So you can have volatilities, you can have skewnesses, you can do all these other weird payoffs into M, so long as you can construct this price and essentially write it in the following form, that you have returns entering into the exponential of M, then you can estimate them using the minimum discrepancy problem that I just described. I mean, the minimum discrepancy problem will ensure, X log X will ensure that M is always positive. I mean, that need not be the case if you're doing minimum variances or using entropies. So the X log X has a very, very nice property that the M's will never go negative. All right, so here is some of the, here. What we found that when we tried to estimate PG using 30 or 90 years of data, the bootstrap error.
Gurdip, we've lost your sound. I think your microphone's come out somewhere.
Oh, I can hear you. Can you hear me?
Now you're good. You're good now.
Okay, sorry. So, over here, when we estimated the fees from 90 years of data, what we found is that the bootstrap standard errors on phi were very, very large. So the data is not really supporting additional time variation. I mean, look, the way that we have it in the formula, it's already time varying with the moments. If you add more conditional variation through these other lagged instruments or the instruments into the formula, they're not really adding that much. I mean, option prices are picking up all the variation that you can think about that should show up in the expected access rate of return. But the end result over here is that your estimate of the average expected access rate of return is not really changing that much. So things were kind of robust. So we can generalize our formula. We can go add more functions for M. We can empirically compare them. We could use additional yardsticks to see what is a better way. But as I said earlier, you can do empirical performance, but the expected access rate of return is not observable. So how do you do empirical performance? So something needs to be thought more over here is how to come up with more empirically viable models of the conditional expected access rate of return, and how do you test them. All right, so this is the first part of the paper that we have. We also dug deeper into this conditional covariance NCC condition. And here, the lemma one is, so here we are just trying to go back and see if is it true that you can have models where the NCC will be violated? Is the conditional covariance term, which is an assumption in Martin, is it an assumption that applies to all M's, all viable M's? Is it a universal condition? So we had to put in some structure or some way to think about this problem and give certain examples, both theoretically and empirically, to show that this may not be a universal property, and hence what we're going to show is that the lower bound can become an upper bound under certain conditions. And if it's conditionally changed, if the sign of the conditional covariance is changing, which it might, then you don't have a universal lower bound. So it means you can have a lower bound in 1 month and an upper bound coming from the discounted conditional variance in another month, which gives rise to the idea that you want to have an exact formula for the expected access rate of return. Bound can be upper bound or a lower bound, it's not clear. So, but if you have a formula, there is no issue like that when you go, I mean, you're not taking a stand on whether the conditional covariance term is negative or positive. So this is the first result that we have, and this is a very standard result. We did not derive it. You may be able to find it in some other papers, but we just formalized it over here, that if x is a decreasing function on D, then the covariance between gx and x will be negative, and the opposite, if g of x is increasing function on D, then it's going to be positive. So here is what we can show in the paper, that if m prime over m plus n plus any integer n over rt is less than or equal to 0 almost surely, then the conditional covariance term will be negative, and vice versa. And then if that's the case, then you get a lower bound, and then otherwise you get an upper bound over here. So if you specialize n equal to 1 to get into the conditional expected access rate of return on the market. So, but the point that we wanted to make over here is that the sign of m prime over m plus 1 over r can change over time. But this condition is not easily testable because this kind of relies on a derivative, which is a local property. But but we still wanted to formalize it and show you certain models in which m prime over m plus 1 over r can change sign, or it can be positive. And these are not unviable models, these are viable models. So let me just go ahead and talk about these.
I feel like I should jump in and give you a warning that we have a hard stop in 3 minutes.
Yes, yes.
Okay.
So we are going to formalize some of the restrictions. So the way we did this is that we looked at the null hypothesis of the STF, and we tried to find m's such that this conditional covariance term is going to be positive. And we use this law of total covariance formula to do this, because you cannot really test conditional covariances. So we're gonna use the unconditional expectation of the conditional covariances. If we can show that the unconditional covariance between m and r is positive, then the NCC will not hold. So here are some of these examples. This is a very nice example because it only depends on the market and the straddle. It's basically saying that your m will depend on volatility and the excess rate of return. This model will say that the m depends on market plus in strangle. These are not unviable models because they would say that when market volatility is high, m is high. Okay, and we can estimate them from the data easily because the alpha, these are linear models. We can just invert the second moment matrix and get the alphas, and they have the right signs. And the third model is basically an asymmetric model of volatility. I'm allowing for volatility to be different in up and down markets. So if you look at the data, and there is another panel C, which I'm not showing, that the conditional or the unconditional covariance in this particular setting, once I've estimated it, they are positive. Okay, yes, it's true that in many of the models where you have monotonically declining pricing kernels, I mean, the conditional covariance term or the unconditional of that will be negative. But there are certain models with volatility where the conditional covariance term or its unconditional expectation will be positive. So it means this is an important viable class in which the NCC is actually violated, which is basically saying we need formulas, exact formulas, rather than bounds, because a negative covariance in a condition is an assumption. Once you make that assumption, the lower bound will pop out. Now, we also developed certain other models where the NCC is not supported, and they are in the paper. One model is basically this the straddle, and here you can see theoretically m prime over m plus 1 over r will be positive, and r is in the positive half line of the gross rate of return is greater than 1. And then here is another model where you have inverse ETF. I mean, you can think of 1 over r. I'm looking at is excess rate of return. And it's basically saying inverse ETF and volatility. Those are the two factors that are entering into M. And you can derive conditions under which the M prime over M plus 1 over R will be positive. And similarly, you have another model which is where the m is a weighted sum of a completely monotone function and an absolutely monotone function. And over here, it's very clear that this m prime over m plus 1 over r will be positive under certain conditions. So essentially, in any model where the conditional covariance m times r can be positive, is going to pose a challenge to the notion of the NCC, and hence you need models, that are of the expected rate of return that are exact formula rather than a lower bound, because lower bound, as we saw, they were only half the size of the estimated conditional expected conditional expected excess rate of return that we estimated from the data. Okay, so I think, thank you for having me over here. I think we have an explanation for the skewness term in the paper. It's a little bit of a convoluted argument over there, but theoretically, the risk neutral skewness is always negative. So it is lowering the expected excess rate of return under P measure. And the reasoning over there has to do with the link between the P measure skewness and the Q measure skewness, and how the two are linked. So you are just taking partial derivatives, and then you're using chain rule, and that's and the sign is actually correct over there. But intuitively, these terms or the higher moments are basically coming from the consistency between the P measure cumulants and the Q measure cumulants, and the weights are actually coming from there. And I'm happy to take any questions later on, and just shoot me a question and I'll be happy to answer.
Great. So one thing, there's a discussion in the chat about whether phi and whether it's constant and how to estimate it, and also the relationship to Martin's approach. But while I was trying to follow that discussion, I forgot to ask Bing Han's question from earlier, and that's a simple question, so I'll ask it now. So can you use your approach to develop estimates of the expected rate of return on an individual stock?
Well, that's a much more trickier thing, because there the densities, the Q densities are a function of a lot of different things. There, yes, you can always write down this conditional covariance term, but I'm not aware of any viable way. Okay, a simple viable way could be to just use a single factor model for the individual stock, and estimate the betas and get the expected excess rate of return from this formula, and get the expected rate of return on the individual stock. But if you have to get the expected excess rate of return on the individual stock from the options on the individual stock and the options on the market, it's not going to be feasible. You're going to cut corners. Plus, there are no joint claims that are traded on the individual stocks in the market. So you cannot really do that. I mean, it's just not feasible. You can use the cumulants. I mean, you can use bivariate cumulants, but what will happen is that all the cross product terms will show up in the bivariate cumulants, and it's not very easy to sort them out. So yes, this approach can be used, what we have in terms of the cumulants, but you have to go to the higher order cumulants, which and here specifically the bivariate cumulants, you'll have to use that.
Okay, so there was kind of a lengthy discussion about phi and estimating phi in the relation to Martin's model, and John participated in that discussion and I think may have answered some questions. So given that we're at the end, rather than me try to summarize that discussion, I think I should let anyone who wants to follow up on John's answers unmute themselves and ask their questions using the microphone. No one. Well, anyway, I'll ask George. Go ahead. Sorry.
I can ask a question. Hi, Gurdip.
Hi there. Yes, Ivan. Go ahead.
I think I just a couple of maybe related questions. Again, I'm pushing this time variant phi thing, because again, to me, it's kind of like the center of this debate whether the risk premium is moving because of the quantity of risk or because of the price of risk. So kind of this time variant phi would be like a price of risk thing. So just two questions about phi, which I also asked there. So one of them, going back to Chris' point as well, that you kind of calibrate / estimate phi using the kind of the whole in-sample data. Then is it that surprising that you in the end can match fairly well at the average returns that you see in the sample? And the second question about phi as well is, going back to this NCC bound, which I completely agree with you, this bound is completely assumed in Martin's paper. I'm completely with you on that. But again, if you go to time variant phi, it would make it even easier for you to reject that, because think about phi being too low. Suppose phi is 0. And in that case, obviously the bound is violated. Just covariance MR is R is just variance of R. It's positive. So we can go into the time variant phi. If phi goes kind of below 1 or small enough, it would immediately reject the bound, even without all this other stuff about like returns and second moments and complicating the M function. Let me stop here.
Yeah, I mean the fee. Option. I mean our approach was like how we do it in finance. We've been doing it in finance for many years. I mean, you have a Black-Scholes model. You have you make simplifying assumptions, but you have a parameter like sigma in the Black-Scholes which has to be estimated. So I mean that's the simplest analogy that I can think of in terms of the fee. Fee is basically measuring the minus the elasticity of the pricing kernel with respect to the excess rate of return, and we are estimating it to be minus 2.27. I mean, you need some parameterization, otherwise this approach is not going to work, because you need to essentially estimate the M, but you don't need to estimate everything about M, but you just need to get one parameter or two parameters that are driving it, and you should be able to get the conditional expected excess rate of return from options. I mean, that was our approach. So, and that's the only way that it can be done if you have to go beyond the bound. I cannot think of anything else. More questions? Are you there? Or did I lose you?
No, we're here. We're here.
Okay.
Is people are being shy.
Yeah, well, I think the discussion in the chat has been very lively. So maybe John answered a lot of the questions already for you, Gurdip.
Okay, good.
So what we can do is maybe just I'll jump in and thank you for having been here. We can have some FaceTime with you in a couple of minutes if people want to stay around. Otherwise, I wish everyone a very good week, and we see you next week for Steve Heston. In the meantime, if you want